In this episode,
that acronym is aimed at some of the people that are actually getting it wrong.
You know, nothing's going to change unless something changes.
How has he got 1.9 million views on this shit?
The D, the I, the C, the K, and the S.
Hi and welcome back to the award-winning Homeowners Q&A Podcast. I'm your host Mars, and today we're tackling one of the most misunderstood yet fundamental aspects of heat pump performance: flow rates, temperatures, and delta T. We brought together a brilliant panel to help us demystify this. We've got Ian Edgeworth from New Perspective Learning Solutions, Nigel from Energy Solutions, and Richard Burrows from Pirate Heating Supplies. Welcome, guys. But before we get started, we'd like to thank Energy Solutions for sponsoring this episode of the Homeowners Q&A Podcast. Energy Solutions are one of the longest established renewable energy companies in East Anglia, specializing in servicing, maintenance, fault finding, and diagnostics of heat pumps. Voted Best Renewable Technology Maintenance Company in East Anglia 2 years running, they've built a fantastic reputation for quality, care, and integrity. As a family-run business, their popular heat pump care plans give homeowners real peace of mind with expert engineers who genuinely care about keeping systems performing at their best. So whether you're a homeowner, landlord, or managing larger estates, the team at Energy Solutions can help keep your renewables running efficiently and reliably. A huge thank you again to Energy Solutions for sponsoring this episode. Right, Ian, well, why don't you get us going today? So let's start with the basics. What exactly is flow rate, and why does it matter so much in heat pump systems and low temperature heating systems?
Generally, for a homeowner's perspective, when you talk about rate, generally we're talking about speed. Flow rates in central heating systems, we're talking about fluid velocity, just how quickly we are moving that fluid throughout the system. It's extremely important, particularly with low temperature central heatings, which are systems that are generally associated with low carbon systems. And it's really an involvement of engineering awareness that flow rates can have a marked comparison to energy output and system performance. So it's critical that we get these flow rates as accurate and as effective as possible.
So, Rich, how does one go about calculating the flow that you need for your system? So, it's all very good and well saying, well, you need good flow. How does one actually calculate that? And is there any kind of metric that allows you to understand how much flow that particular house or property will need?
Basically, you need to know how much energy the room needs, first of all. So normally we do that through a room heat loss calculation. You're moving energy at the end of the day, so you need to know how much energy you're putting into that particular room. So once you know that, then you can actually calculate out your size of your emitter based on the room temperature that you're trying to achieve. And then you need to have, like Ian said, you need to have the correct amount of fluid going into that radiator with the correct delta T to make sure that you're actually getting the correct output for that heat emitter. So there's a mass flow rate calculation that, I just know it in my head. So basically it's the kilowatts divided by 21 for heat pumps. That's as simple as it sort of is. And that will give you a DT, that will give you the actual flow rate in litres per second at DT5. That's how my brain works. I got ADHD. So, it's keeping things simple for me is just the sort of key thing. I know if I need it at delta T20, you just divide by 84. That's how easy the calculation would be. Obviously it is a bit more of a formulated calculation. Basically, it's the specific heat capacity times the actual temperature difference, okay? So that's actually what you are calculating. But that will give you your mass flow rate for that room, and that will be in litres per second. So then if you want it in litres per minute, you just times that figure by 60. If you want it in litres per hour, you times it again by 60. And that will give you actually give you your fluid movement figure that you actually require for that room. So once you know that, then actually you need to do that for every single room. And then you know your total fluid flow for your circuit. Once you've done your heat loss and you've done your whole house heat loss, you know what size emitters you need for every single room. If you then top them all up, you then know what actual size heat pump or boiler or whatever you're trying to design for, you actually know what size that needs to be as well.
So, Nigel, you spend a lot of time going from house to house, doing a lot of maintenance work, coming across systems that are probably not ideal, not performing as they should. How often do you actually find properties where the core problem of their heat pump not running as efficiently or as well as it should be? Can you actually wind that back and pull it back to the fact that the flow rates are wrong?
Vast majority of the occurrences of where people aren't getting the COPs and the efficiency out of the system. I think too much of it now, the installations are done on a turn it on, yes, the rads get warm, happy days, right, home time. It's the big area, I think, for not only for us as a company, but I think the whole industry is to get that understanding of the fact that we're not on Valent or Worcester Bosch boilers that are chucking out 60, 70 degrees of heat, and pretty much you're putting in that amount of heat, you're going to get something out the back of it, regardless of what your flow rates are. With the heat pumps, it's you're dealing with a lot less heat, so therefore it needs to be a lot more specific and a lot more refined, and people need to be looking at these things.
So what do you do if you go to a property where you see that the flows are wrong? How do you actually go about remedying that for that particular homeowner? Is there any quick fixes that you can do?
It's a really tricky one, because it is a situation where homeowner might not be aware of it, as long as they're getting that minimum flow rate to keep the flow switch made or the PCB happy with flow rate is above its minimum. They're not that aware. So when you start looking at, now we're looking at, changing the pipework, putting in extra pumps, draining the system down, it becomes a big problem.
So Ian, what Nigel mentioned there is that he said that certain homeowners aren't actually getting the full benefit of their efficiency out of that system. So is there an interrelationship that exists between flow rate and delta T's and system efficiency?
They're all perfect bedfellows, and they're all directly and inversely connected. Like Richard and Nigel have absolutely nailed it. We can have wide discrepancies with flow rates that would be obvious to an end user, because ultimately it's going to affect performance, it's going to affect running costs, etc., etc. Engineers, for too long, we developed an apathy, because we had, and I include myself in this, I was the world's worst design engineer, because we had these white boxes on the wall that just pumped out high temperature. Customer put their hand on the radiator burns their hand, everyone's happy. We can't continue that path with low carbon and low temperature central heating systems. But where you've got wide discrepancies, where everything's proportional, Richard touched on the mass flow rate triangle and articulated it better than I can. But yes, there's wide discrepancies and there's narrow discrepancies where just a tweak of a flow rate that a consumer could be completely blissfully unaware of can massively affect their efficiency and ultimately their running cost as well.
So Rich, when we had our system originally installed, we clearly, now that I kind of rewind back in time, I can in hindsight see that we've had flow issues. And every time that our installers would come back, they would just put another pump on, another pump on, another pump on, to potentially try and engineer that out of our system kind of being lazy. Is that kind of the only approach that you've got if you just want a quick and dirty fix to get more flow? Is it simply just putting another pump on?
Let's take your system, for example. So you've got a very hard system to overcome. So the original design, when it was done, it wasn't what I don't think anyone did any maths on it. So what you've ended up with is kind of a system that's been added on, radiators that have been put on. And in the end, actually, there's no engineering design behind any of it. So it's all pretty much guesswork. So the issue you've got then is you're not starting with the basics, as you now know, because you've done certain things in your property now and you've had calculations done. It's that basic level stuff. No one's ever done a heat loss properly in your property, heat loss calculation properly in your property. So the issue you've got then, you don't know where you're starting from. You don't know what the emitter size is needed to be. You don't know what your flow rates needed to be. Where we have this issue of guesswork happen, and then all of a sudden you go, oh, this isn't going to work, actually. I've come to commissioning it and I'm getting wide deltas here. I'm not getting enough flow rate through those radiators. What do you do at that point? It's panic stations, right? So engineer wants to get out of that property quickly. And if they just go, you know what, we'll just stick another pump on, or we'll separate it, we'll break the system, put a buffer in, we'll put a pump this side, pump that side, job done. And that's great for them as an engineering solution. It's a quick fix, but for the homeowner, that isn't necessarily going to run as the best design that system could have been, or the most efficient it could have been. There's a few companies at the moment that are going in, putting a buffer vessel in just because it's an engineering solution to get around certain issues on that system, because they couldn't be bothered to design it. They've literally tried to pick the low-hanging fruit, go into that situation and then put a solution in. Yes, it runs, but did it run as efficiently as it could have if it had been calculated? And the answer is unfortunately no.
Building on what Richard said there, when they came to actually commission our system, the manual said that we needed kind of 30 plus liters per minute. When we actually looked at the metering, it was coming in at like 26, 27. And the guy just turned around and go, well, actually, that's fine. So there's clearly a discrepancy between what the manuals say, what the actual commissioning guys are doing. Is that a problem?
Yep, I think it is a problem. A lot of the experience that we've then had is there seems to be a big discrepancy between flow rate ranges in the manual, and then when you're actually on the phone to technical, sort of saying, I don't know, let's pick a manufacturer like a U1 error on a Mitsubishi Ikedan, they're then saying, well, what's your nominal flow rate? Well, all of a sudden, your nominal flow rate is the higher end of that range. So as an installer, you're looking at the manual, they're sort of saying, well, 16 to 24 or 24 to 32. Well, I'm in that range. I'm okay then, aren't I? But then when invariably the installers have moved on to their next installation project, we're then coming in behind, and then all of a sudden, well, actually, okay, well, I'm now really going into it 7-8 plus degree delta T, and then you're looking for doing maybe potentially a warranty claim or something like that, where you're talking to the manufacturer and it's sort of saying, oh, well, no, actually we want 36. You've got 26. So that's the end of that conversation.
What I'd understand there, Ian, is that if the manufacturer requires X amount of flow through that particular system in order to achieve its peak efficiencies, should there not then be stipulating that for every single installation you should have X size pipework or, certain criteria that have to be met in order for that heat pump to stand a chance of actually performing the way that it was actually designed to perform?
Yeah, it's a difficult one because as much as the sector's evolved, we've still got a long way to go. What Nigel's just said is a typical story that you hear on a regular basis when you're reading the Bible of your heat pump, which is your manufacturer's instructions, but then talking to the disciples of the Bible who are then saying that actually that's okay, this is okay. The problem that a lot of people face as well is that manufacturers just want their heat pump working. The stuff that's connected to the heat pump is almost not their issue, right? They just want something that means that their heat pump can hit those efficiencies. The rest of it's just that's someone else's problem. And it can become a very finite issue as well with flow rate, because what's actually happening with the system at that stage are engineers looking at it where they've got optimum demand so they can actually test that in a live situation. As there's zoning in the systems, there's so many variables that come into it as well. And typically when you talk to technical departments of these manufacturers, with the greatest respect, they don't really give two hoots about what's actually happening in the system. They just want to know that heat pump can get rid of energy and then recoup the correct temperature to replenish that energy as well. The rest of it's an afterthought. And this is where it becomes really difficult for guys like Richard and Nigel who are out in the field and your own experience, Mars. Unfortunately, when I don't hit my flow rates, I've got no one to blame apart from myself, because it was me that bunged the system in. But it's very difficult, particularly when it's a retrospective and you haven't been the installer. The experience that you've got where Rich doesn't know what the original calculations were, etc., it becomes ultimately a real headache for the homeowner. And these are experiences that we're trying to dilute, but there's still too many of them, unfortunately, out there.
This isn't just another book about heat pumps. The Ultimate Guide to Heat Pumps brings together the collective voice of over 35 contributors, engineers, designers, troubleshooters, and homeowners with more than 7,500 installations and 585 years of combined experience. It's no-nonsense, practical advice to help you get it done first time. Available now, link in the description. So Richard, we're a bit of a prime example of that because you've spent a lot of time with us looking at our system, and I'm sure that we're not the only kind of system in the country that's actually been done like this. So they put an 18 kilowatt heat pump on our driveway, and we've run 25 meters of pipework into the house, and you said that pipework never ever stood a chance of delivering the flow from that heat pump in order to actually heat your property. That's a manufacturer/installer's fault, right? So can you just maybe explain that for people that are thinking about putting a heat pump in? Maybe they can quiz their installer just to make sure that at least the primaries are of a sufficient size to allow enough flow from that heat pump into the property to give them a chance.
You are relying on installers to get this stuff right. If this was a perfect world, right, we wouldn't need homeowners to care about this, right? Your installer would just come in, he would do the right job, he'd have the right materials, all the design calcs, the right pipe sizes, he'd know what he was doing, he'd put it all in, balance it all out. It would be perfect. Walk away. You'd never think about it ever again. That's how it should be, right? The issue we've got is that when you have a situation similar to yours, so you get the primaries wrong, you're on a loser straight away. If you've got the primary circuits to your home incorrectly sized, you are going to be in a world of pain straight away, because if the head pressure of that pump, so if it's got a built-in circulator or you've designed it to work with a certain size circulator and your primaries are too small and you've now in a world of pain. That circulator isn't going to potentially get the flow rate to the index circuit. I mean, if you've got buried pipework, it's even worse, isn't it? If it's on the surface, you can kind of rectify it. But when it's buried pipework, if it's undersized, you're in a whole world of pain. Without having to dig that back up, you're now actually limiting the amount of kilowatts that you can actually get into that property without exceeding your upper velocity. So when I've talked on a previous episode that I've done with you, we're talking sort of between 0.5 and 1.5 liters per second. Yeah, that's your design limits. So if you're now expecting to push 2 liters, 2.5 liters, 3 liters per second through that velocity, through that pipework, it's not happening, mate. You are not going to get that level of flow through there, not without damage being done or pipework erosion or things like that. So you've got to have, there's a finite detail you need to do at the design stage to make sure all these elements work. Otherwise, you're going to get an underperforming heat pump because it can't deliver the amount of energy it requires to into that house, or you're going to increase pumping or circulation costs. So the amount of energy your circulators are going to use per year is going to be increased. So there's no benefits to getting this wrong. If you get it wrong, you're always going to pay for it in one way or another. And that's unfortunately the sad truth of the matter,
So, Nigel, when you go to these properties where people have got performance issues on their actual systems that you can put down to flow, in terms of getting it done, you need to drain systems down to maybe put more pumps on. Do you offer any other kind of advice in terms of getting them to potentially claim on warranties, maybe try and chase that installer to try and get that job rectified at their cost? Because we know that MCS and the consumer codes are completely useless at actually trying to get those installers back into those properties. What would you advise people that have got flow issues, clear flow issues, with a strategy on how they can potentially get things rectified?
We help as much as we can. We will provide whatever evidence, whatever documented reports that the customer is asking for or anything like that. I think both parties know that they are on a bit of a hiding to nothing because there is no enforcement. The customer can go to the original installer and go, pretty please come back. And then they're into the world of, does the installer have the knowledge that Richard has? And I love the post that you did the other day about, was it the 4 types of incompetency? At what end is that installer on? I mean, the only thing that we've started to try and do in the background is we've started trying to talk to a few litigation companies where you do some form of group litigation order. I personally feel our hands are tied with it all. It's down to the customer as to whether or not he buys into what we're saying to them, because at the end of the day, as Richard quite rightly said, it shouldn't be the responsibility of the homeowner to educate themselves on flow rates and the mass flow rate triangle and delta T's. They should somehow be able to have faith that they're getting competency on the doorstep.
As much as we're preaching doom and gloom just now, there are very, very successful experiences out there and very good experiences. I've trained hundreds of engineers into renewable energy. I try and keep it as simplistic as possible, and we're very, very good in the UK overcomplicating the simplistic and making things more complex than they need to be. To me, the key to a successful deployment of an air source heat pump, for example, is there's 5 key parts to it. You've got design, installation, commissioning, knowledge, and service. Now, there's an acronym in there, and unfortunately, that acronym is aimed at some of the people that are actually getting it wrong. As long as you can remember the D, the I, the C, the K, and the S, then you've got a good foundation there. As much as we don't have a lot of wiggle room, the same as we did with gas boilers, we still do have a bit of wiggle room. When I used to train that acronym, I used to take 5 coins for each part of that and stack them up and swipe them out with a steel ruler. Now, if you take one of those coins out the bottom, the pile will still stand because it's retrievable. But when you've got a completely inadequate design, you've took the foundation out of that system. It was great what Rich was saying about trying to get rid of that energy. It's akin to trying to drive an articulated lorry down a bike track. If you can't get rid of that energy at the foundation, then we've already got problems. You can have the best design on the planet, calculated to the 18th decimal place of energy loss and flow rates, etc. But if you don't follow that design in your installation, then already we've got problems. And also, you can have the best design, the best installation, but if you don't actually set the system up and commission it correctly, then the design and the installation is all for toffee. I can do that as well if you've got the D, the I, and the C right, but the end user doesn't have that knowledge to be able to integrate with that system. The first three parts of the journey have been wasted as well. In my opinion, the best central heating system on the planet is the one that the customer doesn't actually need to touch. Because guess what? It actually works. Right? And it works effectively. Just the problem that there's not many of those out there. And then you've got the problem, as Nigel probably finds from a maintenance point of view, that end users do like a fiddle and they do like to push buttons and have a play about with controls that are sometimes overconvoluted in the first place. And then it's a case of getting people like Nigel or myself from the past back out and going, no, I didn't touch it. But it's all about education. It's all about support. And you need to have confidence in your designer. You need to have confidence in your installer. You need to have confidence in how it's been set up. And you need to be confident as well to integrate with that system the way it was designed to be integrated with.
Quick question for you then, Ian. As a business, we're seeing an inordinate amount of installs coming in from the new build arena. We're sort of seeing that the whole site would have been chucked at City Plumbing or a big contractor like that to do a free design based off of the CAD drawings. We're not too sure about the D there. The install, they're great. Don't get me wrong. They're great pipe benders and pipe installers. So the I's okay. The C, probably not so good. We're coming in at the end of the trail on the S. We don't know what the D and the I was. We can check the C and we can adjust. Our route to market invariably is either leave well alone, and it is what it is, or we do go down the route of putting an extra pump in to see what that will do, because, you know, nothing's going to change unless something changes. I don't know whether or not this was a vicious rumor, but I remember my paths crossed with an Mitzi salesman, where they basically said everybody knew that the pumps that went out on a 14 kilowatt pre-plumbed system simply could not achieve the flow rate required. Regardless, it just couldn't do it. What do you do then?
It is a very difficult one to negotiate. The heat pump sector, as we all know, is still relatively niche, right? We're talking 1.5 million boiler sales a year. Last year we had a record year with heat pumps where it was around about 50,000. The problem with bad news stories in the gas boiler world is they get diluted by the relative ignorance of proper design and installation with a gas boiler because they are so forgiving. But while we still get this niche sector, boilers have factory recalls, parts come out of factories and boilers that are substandard, etc. But because of the collective volume of what's going out there, those get, as I say, kind of almost swept under the carpet. And in the UK, whether it's on social media or whether it's in the news, we bloody love a horror story. We thrive on it. It makes newsprint. It makes gossip. You guys will remember years ago there was a program called Rogue Traders where you had all the guys go in and botching the boilers and charging the pensioner an absolute fortune. Could you imagine going to the BBC and saying, listen, I've got a new idea for a program. I think it's going to absolutely fly. It's called Reliable Traders, and it's tradesmen that actually know what they're doing. No one's going to watch it. But ultimately it's down to people at Mars to get that message out there, and for us to try and continue to fight that good fight, as romantic as it sounds. We need house builders that want to talk to Richard and Nigel to say, listen, we're having problems here, it's causing complaints, how do we eradicate it? Can you come in, give us a bit of advice, give us a bit of support? We need the installers to say, right, okay, it's been designed for 28mm copper, but you know what? It would be easier to fit plastic. And what could possibly go wrong? It's the same diameter. And all of a sudden, we've lost about 3 kilowatts of output just purely because the installer doesn't have that underpinning knowledge of their actions. I'm all for engineers who make a small mistake, but actually have the conscience to say, what did I do wrong? Because I don't want to make that mistake again. The people that I worry about are the people that don't care about the mistakes that they're making, because ultimately, the radiators are starting to heat up a bit and I'm off to the pub and there's your manual. Go forth and conquer it.
If you've got any questions about heat pumps, then you need to join the Renewable Heating Hub forums. You can connect with other homeowners, share experiences, and get advice on heat pumps and renewables. Sign up today and be a part of the conversation. Link in the description. Rich, just bringing this back to flow. So the guys actually touched on the actual units themselves. A lot of the actual heat pump units themselves have got pumps inside of them. And I'm assuming that those pumps won't necessarily be, from a kind of pure design perspective, those pumps might not be strong enough to actually pump and get enough flow throughout the system. So is it almost inevitable that you have to put on secondary pumps onto systems in order to deliver the flow that you need to get your rads up to temperature?
There's two ways to go about it. So you either make sure your design is, so your index circuit is within those design characteristics. So you'll have in a heat pump, you've got a heat exchanger, you'll have a pressure loss across that. Okay, that's the main pressure loss normally in the system. And once you've taken that pressure loss out of the equation, you know what remaining head you've got on that system. So most manufacturers now are putting quite big pumps in heat pumps. Panasonic's, I think they've got like 12-meter head pumps in them. There's some quite big pumps going in heat pumps. So they've been designed to overcome not only the heat exchanger pressure, but actually most index circuits. But where you do have a house like yours, Mars, so where you've got a very difficult house where to get the actual index circuit working and do those 25 meters and everything else, you're going to struggle to do that with one pump, not without going something really stupidly sized. In the design equation, you go, okay, well, maybe actually we're never going to achieve this. We're never going to be able to get DT5 around your circuit in one run, in one open loop circuit. It's not going to be possible. So then you have to look at, engineering solutions. So it's not a fingers in the air and guess. It's right, we'll engineer the secondary side. Okay, so we'll look at that. What DT can we get that operating at? So, okay, we can only get it operating at DT10 successfully to get the correct flows, this, that, and the other. That's a slight compromise you might have to make. So, I mean, in systems like that, if you have DT10 on one side, DT5 on the other, you can blend the fluid perfectly and get the correct kilowatt outputs out. It's one of those unique situations you need to kind of look at and actually engineer a solution rather than go, okay, we'll just chuck another pump on, we'll put what, my questions always are to engineers. Why are you doing that measure? What is that measure going to prevent or help, or what is the cause and effect of each decision that you make? Okay, you're putting a bigger pump on there. What is the engineering? So what flow rate does that give? How many meters head did that give? Is it going to cause any other issues in the system? Is it going to start, wearing the system out? Is it going to start damaging the valves in the system? They're all engineering decisions you have to make. You can't guess this stuff, okay? Heat pumps really expose engineers, and bad engineers as well, unfortunately, because you've got nowhere to go. If you get that design wrong, you've got nowhere to go. So it's really, really important that if these pumps in the system, so take the V-Spin. I think the V-Spin, for instance, the 150A, it hasn't got much residual head left, okay? Once it's gone through their system, because there's an outdoor and an indoor unit, there isn't actually much residual head left. And I think you've spoken to Mark Hall before. He actually had to upsize his pipework to like 35 millimeters to actually get the correct amount of flow based on the amount of head pressure he had left. And you have to make these engineering decisions. Just because it's coming off the heat pump in 28 millimeters does not mean that 28 millimeters is the pipe run for the entire building. It means you still have to design from the heat pump to your index circuit the correct size to get the correct volume of water through it. If you don't do that, then you're going to have to start taking some shortcuts, like putting another pump in, putting some sort of hydraulic separation in. Those are measures that you're doing to overcome issues and problems. If everything's perfect, you shouldn't need those things. But we don't live in a perfect world, unfortunately. And the amount of systems I've had to go out into in the last 2 years, and these have been from new builds to retrofits like yourself, things like that. And I've actually had to do like expert witness statements to get things moving and actually get the actual engineers back, or I say engineers, but that's a very loose term, because they're not engineers, because they're not designing the systems. I think Nigel's been very lucky there with the pipe soldering, because some of the pipe soldering I've seen has been horrendous on new builds. And the problem is bit of copper outside, so it looks good, transition straight onto plastic push fit. And the problem is, like Ian said then, you're reducing your bore size. So now you've actually, where it was meant to be, maybe the specification said 28 mil copper, you've put 28 mil John Guest in. Good luck getting the amount of energy back down those pipes, because it is not going to happen. Like I said, you might get away with it if you've got an oversized heat pump and the pipework was thrown in, but that was oversized anyway. You might get lucky, but 9 times out of 10, there's no luck in this. It's got to be engineered. It's got to be a solution. Otherwise, it doesn't work.
In those instances where you have been involved with those sort of situations, taking outside of the Mars out of the equation for the minute. So in the other instances where it has just been Mrs. Miggins, what's been the solution and what's been the outcome?
That's a difficult one, because 9 times out of 10, if that installer's not coming back, that homeowner's got to pay for it, or someone's got to pay for it. And this is where I've said on a few occasions now, where is this pot of money to help people who have bad installations, who can't afford it? So let's go back to a couple of Eco4 jobs that I've been to and tried to help rectify. They're the most difficult ones, because that heat pump installation was granted and it was free. That homeowner didn't pay anything, but now they've gone from a situation where they had a perfectly good working gas boiler before that was heating their house to the right temperatures, now to a heat pump that's been put in on the same primaries. They thought that would be okay, and now it's not working, and they've had it signed off. It's all under MCS. Who has made these decisions? Who was that commissioning engineer? Who was that person? Because now that homeowner's got to pay for it. And that's the worst situation, I think, this industry at the moment. We talk about being positive, but unfortunately, there's this sector of Eco4 installations at the moment. These people are suffering. They didn't have these heat pumps installed by choice. They might have had a landlord that's had it fitted for them, or they've had the local council come and put it in. They've had this work done in their house, and now they've got a house that doesn't heat up. It's not the heat pump's fault. It was the person, whoever designed that or threw it in, or, like I said, went on Ian's course to get rich quick. That was not the way to go about it. And they're the hardest ones. I'm telling you right now, without like a pot of money or government help with those Eco4 installs, there's going to be a whole world of pain for those homeowners. I love heat pumps. Heat pumps, I think they're amazing. The technology, the efficiencies, what you can do with them if you get the design right, they're amazing. Amazing bits, kids. Way better than a gas boiler, way better than an oil boiler. Those are archaic technologies in what we're trying to do. Moving energies, an amazing concept, but you've got to do it right.
The one thing that we see time and time again on our forums is that there's a lot of homeowners that the heat pump's actually performing as it should, and certain radiators are coming to temperature correctly, and it comes down to those rads actually not being balanced properly. And then it involves the kind of the installer or the engineer to actually come through and actually do that. And the one thing that actually drives me a bit crazy is that when I see instructions like, well, just close all the lock shields, turn them a quarter turn, whatever that's supposed to mean, and trying to get homeowners to try and do it themselves to figure these things out. Is that something that you do on your site visits to potentially kind of find potential issues with flow through rads? Does it sometimes come back to just poorly balanced systems?
It's quite funny actually, because there's a guy on YouTube, and I was, you look at your YouTube channel, don't you? You go, oh, why didn't my video that said it correctly not get as many views as the guy that went round, did quarter turns on everything and said, yeah, that's how you balance your system. Didn't mention flow rates once, or the correct, flow to each radiator or anything like that. I'll start at the beginning, close all them off, and then the one at the end, just open it up a little bit more. I'm just like, how has he got 1.9 million views on this shit? You know what I mean? I was like, well, how has he done that? Oh, just, mass flow rate calculations and, emitters. And, I was like, oh, maybe I was wearing handsome enough. I don't know. Maybe it was the beard. I don't know. I don't know what it is. Maybe he was just better looking than me. I don't know. But it's just ironic, isn't it? It's just the shit information out there that gets the most views. And all these people have got, oh, brilliant. And they see them commenting, oh, that's great. Yeah, my radiators now work. Well, yeah, because you've just restricted the flow on all the or the front, but come the -5, you're going to be cold probably. Do you know what I mean? And you're going to go back round and tweak them all back open because you haven't got your flow rates you needed. It's mad. I find it madness.
Ian, wrap this episode up for us. So what does good practice look like for maintaining balanced flow across an entire system?
A system that a customer is actually happy with, a customer who doesn't need to worry about Scots and Cots and delta T's and flow rates, etc. They are just blissfully happy in the fact that they've got an economic, efficient, comfortable home that isn't costing them any more than it should do because the D, I, C, K and S has been successful.
If you've got any questions about heat pumps, then you need to join the Renewable Heating Hub forums. You can connect with other homeowners, share experiences, and get advice on heat pumps and renewables. Sign up today and be a part of the conversation. Link in the description. So a massive thank you to Nigel, Ian, and Richard for helping us decode what's often seen as one of the dark arts of heat pump design. And a huge thank you to Energy Solutions for sponsoring this episode. They're a family-run business with over a decade of experience in renewable servicing, maintenance, and installations across East Anglia. If you enjoyed this episode, make sure that you subscribe, drop us a comment, and join the discussion over at Renewable Heating Hub. Until next time, stay warm, stay green, stay tuned. Goodbye.